Hello everyone, hope all of you have started Pythagorean triplets. In the past session, I have explained what are primitive Pythagorean triplets and Pythagorean triplets. If they are primitive Pythagorean triplets, they must be prime to each other. Number one, and two legs are of opposite parity. If one of them is even, the other one must be odd. And hypotenuse is always odd. Okay, today's class I'll be discussing how to generate Pythagorean triplets. Are they infinite in number? Is there any restriction on those generators? And what is the application? Why are we going to do Pythagorean triplets? I'll be explaining all those and some application in geometry and algebra. If possible, I'll be discussing today. Stay tuned till the end of the class. Today's session will be started with the revision of concept of primitive Pythagorean triplet and how to generate those primitive Pythagorean triplet. Before that, let us remember the properties of primitive Pythagorean triplet which we have proved in the previous session. Number one, if those three primitive Pythagorean triplets you have taken as A, B and C, then number one of them will be even and the other one has to be odd. I mean, if you have taken A, C, B, 4, then C equal to 5, that we have seen. And the integers, those are all coprimes. There is no common divisors among A, B and C. Parity. A and B have different parity, which I have told you already here in this case that A and B are of, one of them is odd, the other one is even. So they will have different parity and hypotenuse is always odd. See, whatever doing it here on A, B and C, that is applicable to geometry in case of right angle triangles. If there is a right angle triangle whose sides are primitive Pythagorean triplet, A, B and C, say A and B are called legs and this is a hypotenuse and the relation is A square plus B square equal to C square. These are primitive Pythagorean triplets and there may be many similar triangles, I mean infinitely many similar triangles whose sides are common multiples of A, B and C. There may be, see, if these sides, if these values you have taken A equal to 3, B equal to 4, then C equal to 5. This triangle whose sides, why I am saying all these things, because here we are relating geometry and algebra. Before that, I have to remind you something and then we can proceed. So, if you have taken this one 9 multiplied by 3, this one 12, this is going to be 15. What you have done there? Each multiplied by 3 over there. So, this is 9, this is 12 and this is 15. These two triangles are similar to each other. So, once you get a primitive Pythagorean triplet, based on that, infinitely many triangles can be formed. Now, question arises whether those primitive Pythagorean triplets are infinite in number or there is a limitation of there is a limitation of primitive Pythagorean triplets. I mean generation of these triangles will be stopped or not? Primitive Pythagorean triplets are limited in number or not? Let us disclose all these facts one by one. Before that, little bit of application of primitive Pythagorean triplet. I remind you, they have application in various fields like geometry, constructing right angle triangles, already little bit of discussed, number theory, automatically, because we are going to explain geometric property of right angle triangle with the help of numbers. So automatically there will be a very good relation with the number theory, this Pythagorean triplet. And I'll show you how it helps to solve IC/CMI problems. It helps to think you. It has application in cryptography, but we are not going to discuss it today. I'll discuss in some other session how Pythagorean, primitive Pythagorean triplets or Pythagorean triplets can help you to understand cryptography. Understanding generation and properties of primitive Pythagorean triplets provide insights into fundamental relationship between numbers and their geometric representation. These triplets are not only mathematically significant but also have a practical applications in various scientific and engineering fields. So in broader sense, there are many ways to apply the concept of Pythagorean triplets. But today's session will be doing only on primitive Pythagorean triplets, their generation and some interesting problems. Let us start with one simple problem. Because numbers and geometry you are going to relate, you must think whether the sides of a triangle, right angle triangle, being AP or not. Can we generate, how many triangles can be generated whose sides are in AP and they are primitive Pythagorean triplets. Okay, so let us start with these questions. How many right angle triangles are there whose sides are PPT, primitive Pythagorean triplets, and in AP? This is just warm up before you start anything new here. Let us answer these questions. How many right angle triangles are there whose sides are PPT and they are in AP? So, standard AP, you take A minus D, A and A plus D. Obviously, A plus D is the largest one. This is going to be the hypotenuse. This is A plus D. Legs are of this form, A minus D, A. This is right angle. So, the relation among these three sides going to be A plus D whole square equal to A minus D whole square plus A square. This implies A square 2AD, D square equal to A square minus 2AD plus D square plus A square. So this implies you cancel all these facts, A square, D square, A square, D square get cancelled. So if you take them on the same side, it is going to be A square, transfer all on right side, this is going to be a square minus 4ad. Okay, so in this equation a square minus 4ad equal to 0, there are two options only. What are those options? This implies a into a minus 4d equal to 0. So a equal to 4d, a can't be equal to 0. Okay, the length of side becoming negative. Now by taking a equal to 4d, for a equal to 4d, we have three sides, 4d minus d, 4d and 4d plus d, 3d, 4d, 5d. Obviously these three are PTs, I mean Pythagorean triplets, but they are not primitive Pythagorean triplets, isn't it? Because d is a common factor, as d divides all. So for PPT, what we have to do? For PPT, from these three numbers you have selected, d must be equal to 1. Therefore, three sides are 3 unit, 4 unit and 5 unit. So answer will be only one triangle is there. Answer that for one triangle only, sides are in AP and they are all PPTs, primitive Pythagorean triplets. So question may be there that how many are there? Your answer is 1, and this is the triangle whose common difference is equal to 1, and this will answer you for PPTs when you are forming a right angle triangle. Then in one case only there will be a triangle whose sides are conjugative integers. These are conjugative integers also. This is the one case. So no other case you will get primitive Pythagorean triplets. They form the sides of triangle and they are in AP. Now another question arises here. Number 2. Can the sides of triangles with PPT be in GP? I mean, can they form a GP? Those three PPTs, A, B and C. If you keep all these things in your mind, many problems can be solved later. So we'll think about it whether PPTs can be in GP or not. Sides of triangle can be in GP or not. This we are going to think. So you take the length of sides as ABC and common ratio equal to R. So R will be equal to B by A, C by B. This implies B equal to AR, C equal to BR, that is AR square. Okay. Now this is A, this is AR square and this is AR. So as they are Pythagorean triplets, A square plus AR whole square going to be AR square whole square. This implies A square 1 plus R square, R to the power 4 So minus r square minus 1 0. So r square is going to be by Siddharacharya method 1 plus minus b square minus 4ac by 2a. Clear? 1 plus minus root 5 by 2. So r is going to be under root of root 5 plus 1 by 2, because you will ignore negative sign, then r will be a complex number if you keep negative sign over there. So r equal to under root 5 plus 1 by 2 and whole root. This is an irrational number. Root 5 is irrational. Okay? Root 5 is irrational. So this thing going to be irrational. Clear? This thing going to be irrational. So there cannot be any triangle whose sides are in GP. I mean any right angle triangle whose sides are in GP. PPT is a different issue. But they cannot form the sides of a triangle if numbers are in GP. Because the most important property is that they must be all natural numbers. Alright? Now we will go for generating Pythagorean triplets which are primitive. I mean, in this process of parameterization, we will keep always in our mind that two legs, I mean length of sides of two legs, they have different parity and the hypotenuse is always odd. So, what can be those primitive Pythagorean triplets, and they are generated by one or two variables? This we are going to discuss one by one. The generating formula for primitive Pythagorean triplet ABC given by m square minus n square a, b equal to 2mn, and the value of c equal to m square plus n square. But never forget to mention the condition over there. M and n are coprime, m greater than n, m n are coprime. M should be greater than n because otherwise this will be negative. Mn must be coprime. Coprime means they don't have any common factor other than 1. Now before we start anything, let us see whether they can form primitive Pythagorean triplets or not really. Just obeying this condition, m greater than n and they are coprime. You take m equal to 4, n equal to 3. What do you get? A equal to, that is 7, b equal to 2 into 4 into 3, that is 12, and c equal to 4 square plus 3 square, no, this is 24, and this is 25. Obviously, they obey the relation that 7 square plus 24 square equal to 25 square. You know, these formula are given by the generating function, not function. The generators for PPT was given by Euclid. It was not given by Pythagoras. Euclid did research work and he claimed that these are the primitive Pythagorean triplet. But there is a proof also. This proof I will definitely give you, but before that, let us see whether those important properties are satisfied or not. Number 1, m square minus n square and 2mn have different parity or not. Number 3, m square plus n square is always odd or not. First we prove that A, B, C, they do not have any common factor. Let us assume that GCD of ABC is equal to D. This implies that D divides A, D divides B, and D divides the third one also. So this implies D divides m square minus n square, D divides 2mn, and D divides m square plus n square, isn't it? Now just look at these two. D divides m square minus n square, D divides m square plus n square. So what does this imply? D must divide m and D must divide n, because both of these will imply that D divides m square and D divide n square, isn't it? That's why they divide the sum of the squares and difference of two squares. Now if let P be a prime divisor of D, let P divides D. This implies P divides m square and P divides n square. Now since P is prime, this will imply that P divides m and P divides n. But mn are coprime. That we have claimed. It should be, they must be coprime. But what you have got here? P divides m and P divides n. GCD of mn is 1, therefore P doesn't exist. I mean the GCD of mn must not exist over there. So D must be equal to what? D must be equal to 1. So this implies therefore D must be equal to 1. This implies GCD of ABC is equal to 1. Okay? This is one thing. Next one, mn you said coprime. How to prove that GCD of AB equal to 1? There may be a GCD between them. But A is what form? A is equal to m square minus n square and B equal to 2mn. We have claimed that mn are of opposite parity. Mn are of opposite parity. One of them even, one is odd. This is always odd. A m square minus n square, one even square minus one odd square is always odd. Now whatever values of mn you have taken, this is always even. Agree or not? This should be always even. So this implies that AB, I mean m square minus n square and 2mn also have different parity. Clear? Hope you have understood. So these three numbers, A equal to m square minus n square, B equal to 2mn and C equal to m square plus n square, obey those two initial conditions that they are coprime, and secondly A and B also have different parity. And as they have different parity, this C is going to be always odd. So this is the condition we require. A and B are of different parity. A and B are of different parity. And C is always odd. And the third one, do they really form the sides of Pythagorean triangle? So let us verify. A square plus b square, if you do it with these two numbers, this is going to be m square minus n square plus 2mn whole square. This is m square plus n square whole square. Okay, and this is equal to c square. This implies, because it's a right angle triangle, so c must be equal to m square plus n square. But there is an elegant proof from number theory consideration also, not by going these steps. This is also done by the help of number theory, but the thing is that we have proved indirectly, that we have claimed that these three are Pythagorean triplet, so they are obeying the property, so our consideration is justified. But there are some elegant proofs of generators of Pythagorean triplet. When I get the scope, I will definitely show it to you. Now, let us find some applications of it. What are those applications? Question automatically arises. If you have got Pythagorean triplets, those who are primitive in this form, why they can't be consecutive? Why they cannot be consecutive odd integers? Let us first prove that whether a and b can be consecutive or not. Let us prove it first. Can a and b be consecutive? This is the question. Can a and b be consecutive? Let's see. Then a plus 1 going to be equal to b. What does this imply? M square minus n square plus 1 equal to 2mn. This implies m square minus 2mn plus n square equal to 2n square minus 1. This implies m minus n whole square 2n square minus 1. Or you can write m minus n whole square plus 1 square equal to 2n square. Okay. What does this mean? You can get many derivations from there which claims that this is not possible at all. Here we can write that m minus n whole square minus n square is equal to n square minus 1. Isn't it? That is m minus n plus n. M minus n minus n is n plus 1, n minus 1. That is 2m minus n into minus n equal to n plus 1, n minus 1. See, left hand side always going to be negative, right hand side is positive. This is not possible. To m minus n, we have assumed that m greater than n, no? So m greater than n means this is positive, but this thing negative. Right hand side, what do you get? It's a positive number only. N is always greater than 1. Primitive Pythagorean triplet. Even if it is equal to 1, then also the relation is not obeyed. So a and b cannot be consecutive integers. Now for b and c, can they be consecutive integers? B is what? 2mn. C is m square plus n square. So b plus 1 must be equal to c. This implies 2mn plus 1 equal to m square plus n square. This implies m square plus n square minus 2mn equal to 1. Therefore, m minus n whole square is 1. You don't consider negative integers, so square root will give you 1 only. Okay? For m minus n equal to 1, this implies that m equal to n plus 1. So if m equal to n plus 1, a is going to be what? M square minus n square, that is n plus 1 whole square minus n square. This will be 2n plus 1. B is going to be what? 2mn, 2n n plus 1. And C equal to what? M square plus n square, that is n plus 1 whole square plus n square, that is 2n square plus 2n plus 1. Hope you have understood. So now when B and C are conjugative integers, we got integers in this form. That is, one of them is 2n plus 1, the other one 2n n plus 1, this is odd, this is even, and this one is always odd, 2n square, 2n plus 1. Okay? Now for n equal to 1, what do you get? This is 3, this is 4, and this is 5. Clear? Any n you take over there. N equal to 2 if you take, what do you get? For n equal to 2, this is going to be 5, this is 4 into 3, 12, and this is 8, 4, 1, 13. This way you will get this kind of Pythagorean triplets where you can see they are all conjugative integers in case of B and C. This one need not be. This is the one case only, no? But here it is not. Okay, let us do with one more. N equal to 3. This is going to be 7. This is 6, 4, 24. And this is going to be 25. These two are going to be conjugative. Hope you have understood. So, this is possible that B and C are conjugative integers. This way, if you try to generate, you will get many. So, going towards to prove that PPT is also infinitely many because n is a natural number. Okay. Now a question arises, can they be conjugative odd integers? Can they be conjugative odd integers? Conjugative odd integers for A and B not possible. Why? Because they have different priority. Not possible for A and B. For B and C, we'll check it. First we check with A and C. Let A and C be two conjugative odd integers. A and C we have taken two conjugative odd integers. It is well established that C is always odd integer. Okay? Now the form you try to remember that A is what? M square minus n square, B 2mn, and C equal to m square plus n square. Conjugative odd integer means A plus 1 should be equal to C. C we know odd. So this may be odd, may be even. This time we are assuming that they are both odd. So A plus 1 must be equal to C. This implies that m square minus n square plus 1 equal to m square plus n square. What does this imply? M square, just a minute. No, they are not conjugative integers, they are conjugative odd integers. So this will be plus 2 over there. What does this imply? M square get cancelled. So 2n square equal to 2. Therefore, n square equal to 1. No negative integer, n should be equal to 1. For n equal to 1, what do you get? A is equal to m square minus 1, b is equal to 2m, and c is equal to m square plus 1. Let's see what kind of numbers are generated over there. This is for A, this is for B, and this is for C. You don't take m equal to 1 because to B, this is always even. You can see that B equal to 2m, no? So B is always even here. So this A has to be odd. B is even, C is always odd. So what value of m you will start with? We are taking, say, m equal to 2. Then A is going to be m square minus 1. This is 3, 4, 5. We got the first one. Now we take m equal to, say, 4. Why not 3? Because 3 will make this one even. But this is well established that B will be even, so A has to be odd. That's why we are taking even numbers here. For M, we take even numbers only. Otherwise, they both will become even. That is not possible. They are of different parity, So we must choose it here. That m equal to 4, this is going to be 15, this is 8, and this is 4 square plus 1, that is 17. Next, what can you choose to generate these kind of numbers? So they are two consecutive, because consecutive odd, 3 and 5 two consecutive odd. 15 and 17, they are two consecutive odd integers. Now let us take just one more. M equal to 6. This is going to be 35, and this is going to be 12, and this is 37. You can check 35 square plus 12 square is always 37 square. So m is infinitely many. I mean those even integers, even positive integers, even natural numbers. So again you can state that these numbers also going to be infinite. So primitive Pythagorean triplets are infinite in numbers. Primitive Pythagorean triplets, they form triangles infinite in numbers. Triangles similar to them must be infinite. So Pythagorean triplets really form infinitely many triangles. Let us relate Pythagorean triplets, primitive Pythagorean triplets, with geometry again. Prove that in radius of a primitive Pythagorean triplet, in radius of a triangle formed by primitive Pythagorean triplets is a positive integer. Always it will be positive integer. How to prove this? So assume this angle 90 degree, this one m square minus n square 2mn, and this is m square plus n square. How to get in radius of this triangle? You have to draw a in circle over there which will touch all the sides. If you take the center of the circle at this point, then this is in radius. I am not going to prove the formula now, do I? Okay, I give you a short proof of it also. That area of triangle delta is what? Area of ABC is nothing but area of OBC, area of OCA plus area of OAB. Area of OBC is what? This side length is A, this one B and this one C. This is going to be half AR, half BR, half CR. Half into A plus B plus C into R. But this is semi-perimeter, you know. So delta equal to S into R. R going to be what? Delta by S. Delta divided by S. What is delta over there? Two legs are given there. Half into 2mn into m square minus n square. How to find S over there? S is m square minus n square, m square plus n square 2mn. This is nothing but 2m square plus 2mn. Okay? M square minus n square, m square plus n square 2m. So you take 2m common, it is going to be m plus n. So semi-perimeter is half of this. Half of this thing, that divided by 2 means it is going to be m into m plus 1. Put m into m plus n over there. So these two get cancelled, mm also get cancelled, n into m plus n, m minus n by m plus n. Clear? These two getting cancelled. This is going to be n into m minus n. Clear? So radius you got r equal to n m minus n. Since n and m both are integer and m greater than n, this implies that r is equal to a positive integer. Understood? R is equal to a positive integer. Question is how many triangles can be formed? Let me discuss it right now. Now m greater than n and they are prime to each other. So what does this imply? M minus n and n, they have opposite parity. Okay? So there will be two options over there, r equal to n into m minus n. This implies that m minus n equal to 1, m minus n equal to 1, n equal to r, this is case 1, and number 2, m minus n equal to r and n equal to 1. So therefore we can state that there will be two triangles over there under this consideration, that where the end radius of the triangle is going to be an integer, that m minus n 1 and n equal to r, or m minus n r and n equal to 1. So if there is any problem in understanding all these concepts, please write in the comment box or contact with me directly. These are all free classes. I will be able to discuss with you. Thank you.